All right, so we're taking a look at the second one of our videos in the series on acid-base reactions. On this one, we're going to take a look at neutralization, which really isn't, I don't think it's going to be too challenging a concept. If you're going to follow along, you might want to have your calculator available for today, since we'll do a couple little quick math problems in here. So neutralization reactions. A lot of students know that when you mix an acid and a base together, they neutralize each other. Well, what does that mean, right? So first thing I want to remind you is that when we are talking in this particular context right now, we're generally going to be dealing with these things as strong acids and strong bases. In other words, strong acids and strong bases are those that ionize completely, that separate out into their component ions and don't stay kind of bound up. Weak acids are the ones that stay bound up. Their math is a lot more challenging. So we're going to kind of get around avoiding that situation by either using only strong acids and bases, or if we use a weak acid, we will combine that weak acid with a base that it is so strong, the base is so strong, that again, it will help assist the weak acid in releasing its hydrogen ions. So again, when we're talking about strong and weak here, we're talking about ionization. We're not talking about concentration, different idea. So again, this is about neutralization reactions and what happens when we put these things together. So the easiest way to kind of conceptualize what a neutralization reaction is at this point is to think of it just as a double displacement reaction, because that's exactly what it is, with to some extent. For the level of work that we are doing, that's a great way to sort of visualize what's happening in here. So it's a double displacement reaction, which just means that we're simply swapping ions between the two, right? The positive ion from one is going to end up with the positive ion of the other one. So we end up with this combination and that combination, sort of the inside-outside phase. So in this particular case, hydrochloric acid and sodium hydroxide, we get NaCl and HOH. Now, what's important about this is to think about physical states. Solubility becomes kind of an important issue here. These are dissolved in water. These are dissolved in water. And guess what? Sodium chloride is also soluble in water, AQ, and water is, well, water, liquid water. It's not dissolved in water. You can't dissolve water in water. It's just water. So what's interesting about this sort of double displacement reaction is that there's really nothing visible, nothing to see. There is a product that forms, and that's the formation of liquid water is our driving force here, rather than the formation of a solid precipitate. Remember, back in double displacement reactions, we'd have two ions that would come together and were so into each other that they would simply settle to the bottom. Well, in this particular case, we get hydrogen and hydroxide ions coming together, and they are forming this product, water. But it's surrounded by more water, so you can't see it. And it's not like the volume goes up or anything along those lines. A lot of times, the only really measurable idea that something's happening here is a change in temperature, if we don't have something else to give us a hint that a reaction is going on. So anyway, double displacement reaction, pretty normal. When we generalize it, and you'll see a reaction kind of like this pretty commonly, HA plus BOH. In other words, it's an acid, because acids have hydrogen in it, and this is a base, and a base with hydroxide in it. We're using the simple cases of these. When we bring these together, we get the A and B together, and we get the H and the OH together. So we literally get BA, B's the cation, A's the anion. I know it's like everyone wants to write it as AB. And we get HOH. So again, with this one, this thing right here, this ionic compound, just like this one up here, is called salt. That's what that compound is. A salt is any ionic compound that can be formed from an acid-base reaction. That's the definition of what salt is. The most famous salt is, of course, what we call table salt, sodium chloride. So that is a salt, but there are lots of other types of salts that are out there as well. Again, any ionic compound that can be formed from an acid-base reaction. And then our other product is water. So literally, anytime, I don't have to put air quotes around that, anytime we do an acid-base reaction, your two products are salt and water. That's the definition of it. If we take a look at the net ionic equation for this, by the way, remember that this is H plus and A minus, and we've got B plus and OH minus, and they combine to form a salt, B plus and A minus, and liquid water. Now, liquid water is molecular. It stays together. It is that product that actually drives this reaction. So it does not get separated out. It is not ionic. So if you take a look at our net ionic equation for this, it turns out that the ions in the salt are really just spectator ions. They've got B on both sides. You've got A on both sides. So literally, the net ionic equation for every acid-base reaction is this: H plus and OH minus produces water, HOH. That's what's really happening in every single acid-base reaction, especially neutralization reactions. And now you can see why we would call this neutralization. We're taking the acidic character, we're taking the basic character, and we're locking those two things together in liquid water, which is neutral. So acid-base reactions. So typically these are in the guise of basically just stoichiometry problems. Don't overthink these too much for the purposes of what we were doing. If you get into higher level chemistry, there's definitely more crazy stuff that we can end up doing with it. But for the purposes of chapter 4, these are essentially just double displacement stoichiometry problems. So I'm not going to do this in full exquisite detail simply because of time. And hopefully you know how to do these, but I'll kind of get it set up for you so you can kind of get going on there. So again, here's the case. This is vinegar. This is acetic acid. And it's reacting with potassium hydroxide. So with this, this is that case that I mentioned earlier. Vinegar is technically a weak acid, but potassium hydroxide is such a strong base that it will cause complete ionization of this. So our net ionic equation is still going to work out the same way we want it. So the first thing that you want to do is you want to make sure that you predict your products and balance your equation. In this case, it's a pretty easy one to predict. Here's our salt. It's KCH3COO, potassium acetate, and water, H2O, or HOH. Those are our two products for it. So if we want to actually do the reactions this way, it's literally just set up as a stoich problem. 75 milliliters. This is 0.20 molar. And we use our molarity equation. Molarity equals moles per liter. Or we do molarity times liters equals moles. And then you solve it as a stoichiometry problem. When it says something like this, like how much, you could probably answer this in grams the way it is right here, or you could answer it in moles. Or more commonly, they'll give you like a volume, like what quantity of it you need. But in this particular case, I just wanted to set up the idea. So I didn't put a particular molarity in there because that would really make a difference for what we're trying to do. So anyway, we would do something along these lines, 0.2 moles. So molarity, if I could do my little equation there correctly, times 0.075 liters. Don't forget to convert it to that particular case. 0.2 times 0.075 means I have 0.015 moles of potassium hydroxide, or 0.015 moles of base are present in this particular reaction. So how much of this other stuff do I need? Well, if you take a look at this, I don't think we need to do the stoich problem, but we can. If we've got a 1-to-1 ratio on this, that means that if I have 0.015 moles of potassium hydroxide, that would take 0.015 moles of sodium or hydrogen acetate or acetic acid would be needed, or something like that. Required to neutralize that. And then again, you could either convert this to grams if you had it in solid form, or again, you could use a molarity equation if you were given a molarity of this and converting it to volume. So again, neutralization reactions, literally just stoich problems with solutions. Don't overthink those too much. Keep in mind that with this, kind of going the next step, and this one I will work out in a little bit more detail, we do have a limiting reactants issue with this. Neutralization, that word is a little bit misleading because it kind of gives you the idea that if you take any amount of acid, any amount of base, throw them together, it's going to magically neutralize somehow. And that's not true because we have limiting reactants. I know that if I put an equal amount of these two present, equal amount of the critical stuff anyway, that I would get a neutral solution. But what if I put extra base in there? You know that your final solution is going to be basic. Or if I put a whole bunch of extra acid in there, my resulting solution could be acidic because there's this thing called limiting reactants and excess reactants. And that's what this kind of equation kind of helps you think about. So with this, your first step, again, figure out what your products are. Again, it's going to be a salt and water. In this case, it's going to be calcium phosphate, PO4 2. Phosphate's a 3- charge and calcium's a 2+. Just as a reminder, that's where these subscript numbers are coming from. And water. So there's our two products. Don't forget, you do need to balance your equation. They're not always one-to-one, and this one is specifically not one-to-one. So if you take a look at this, I've got 2 hydroxides and 3 hydrogen ions. I'm going to save us a little bit of time. The lowest common multiple of 2 and 3, because they're in the same thing, has got to be 6. So this is going to be like this. I know it's like, why, how? Trust me on this one, you can work out the long run when you have it on pencil and paper. So this is going to work for you. And then if you take a look at this, we've got 3 calciums, 2 phosphates, and 2 phosphates up there. So this equation is balanced. So how do we figure out what we're going to do on this? We've got 100 milliliters of the 0.2 molar base, 100 milliliters of 0.2 molar of our base, and then we have 80 milliliters of 0.25 molar acid. So this one isn't really easy to eyeball it because we've got all these coefficients in here and it makes it a little bit awkward. So treat this like any other limiting reactants problem. So again, remember when we do our molarity equals moles per liter, we usually end up rearranging this and using this equation like this: molarity times liters equals moles. That's what we really want, is to find the number of moles of each thing. So here's how this is going to work. So we would do 0.2 times 0.1 would give us the number of moles of base, and this would be 0.25 times 0.08 would give us the moles of acid. All right, so 0.2 times 0.1 gives us a starting value of, I know that, why am I doing this? 0.02 moles of calcium hydroxide, and 0.25 times 0.08 gives us, what is it, 0.02, oh really? 0.02 moles of acid. Okay, now we just do the stoic from here. All right, so what is this going to look like? Okay, I'm going to erase this and give myself some space. We have 0.2 moles of each. So which one of those is going to be our limiting reactant? You might be able to start to predict what this is going to be. 0.02 moles and 0.02 moles. Okay, so set up your 2 equations. 0.02 moles of base, moles of calcium hydroxide. And then we're trying to figure out, let's see, what does it say? What will be the relative pH? Okay, relative pH. By this, all we're saying is, well, what do we have left over? Is it going to be acidic, basic, or neutral? That's what we want to know. So what are we going to have left over? I'm going to go towards a product. I'm going to go towards this one just because it'll make my life easier to see which one it is. Or you can go from one to the other and see which one uses up. There's a couple of different ways that you can address this. So I'm going to go, like I said, towards a product and figure out which one my limiting reactant is. And if I know which one my limiting reactant is, I know which one my excess reactant is. So I'm going to go 3 moles. This is my mole to mole step, right? 3 moles of calcium hydroxide will produce 6 moles of water. I don't even need to go to grams at this point because really all I care about is identifying which one is my limiting reactant. And 0.2 moles of the other one. Sorry about that. The H3PO4. Now I'm dealing with my acid. And I know that 2 moles of that, of H3PO4, my mole to mole step, is going to produce 6 moles of HOH. So I can tell right now kind of which one it's going to end up being. I'll do the math really quick just so we've got our answer here. 0.02 times 6 divided by 3 is 0.04. 0.04 moles of HOH or H2O. And the bottom one, 0.02 times 6 divided by 2 is 0.06 moles of HOH. So what does this mean? Okay. Well, so we would always pick our smaller answer. This one right here, that's our theoretical yield of water. I could make 0.04 moles of HOH. It's my theoretical yield. If that's my theoretical yield, that means that this calcium hydroxide right here is our limiting reactant, right? That's the one that ran out to produce our smaller quantity of water, which means that this is my excess reactant. I've got some of this left over. So what does that tell you about my final pH of my solution? If I combine these 2 quantities together, all of my calcium hydroxide gets used up, but I have a little bit of H3PO4 left over at the end. It's my excess reactant. Therefore, my final solution, my relative pH, is going to be acidic. It's going to be on the lower end of this. We haven't talked about the pH scale yet, but it's going to be acidic because the acid is my excess reactant. Okay, I think one more here. The last thing I want to mention about doing neutralization reactions is sort of an introduction to how we do neutralization reactions. How do we tell exactly when a solution is neutral or not? And there's two major techniques. One would be to have a pH meter, literally stick something that looks like a digital thermometer, a really fancy one, in here and have it read the pH to us, and we could tell exactly when it's neutral. They're a little bit fidgety, but they do work, quite precisely if you take your time with them. More commonly in a lab, in a chem lab, we do this process called titration, where we have a solution here that's going to turn color, basically, or acidically. It's going to turn color when we get to neutral. We have a burette, which is basically a really fancy dripper that's full of a solution that we know. Then we have a flask that is full of our unknown that we're trying to figure out how much of that we're using up. And then we have something in there that would be an indicator, and an indicator is the thing that would change color to let us know when we've gotten to that neutralization point. So with this, again, in terms of what the setup is, it's still just a stoichiometry problem. This is just how we know when we get to. So typically what we're trying to do is figure out maybe what is our molarity of this sort of thing. That's what we're trying to determine, or something along those lines. So what we do is up here, see how this is base of known concentration. That's our standard solution. The one down here is our unknown. Usually this is the acid, usually. We can reverse those. We could have a known acid up in the burette, and we can have an unknown base down in the flask. That's totally fine. And then we're going to slowly drip this base into our acid, drop by drop, so that we can keep track of the volume that's happening. So just like was described in the previous problem, we're going to keep track of how much volume of base was used for this thing to go exactly neutral. And how do we know it goes exactly neutral? Because we're going to use an indicator, a color-changing chemical that turns color at its endpoint, right really close to the equivalence point, and that means neutral. So those are some fancy words kind of all thrown together here. So let's look at an example of what that is. So here's an example of kind of our setup. So we've got a 10 milliliter sample of vinegar, and it's titrated with this horrible random solution of NaOH. That's our base of known concentration. In this case, we're going to use NaOH. Why is it such a weird value here? Because a lot of times when we do these at first, we have to know the exact concentration, not just sort of a random concentration. So this is actually pretty realistic. So we're going to have CH3COOH. There's our acid, plus our NaOH, right? And we're going to make sodium acetate, CH3COO, and water, HOH. So there's our equation that we're using. That's our double displacement we're doing. We've got a 10 milliliter sample of this, and we know some other things. So we don't know. What we're trying to find is the molarity of this. What's the concentration of the vinegar? That's usually what you're trying to figure out. We're using this, exactly 16.58 milliliters of hydroxide was used. So in other words, this would have dropped. You would have dripped out 16.58 milliliters of it. And we know this exact solution. It's been standardized for us, 5062 molar. Come on, there we go. So at this point, once you get the idea of this is just a Stoic problem. This is literally like a moles to moles kind of conversion. So we would literally do our thing, molarity times liters equals moles. We would figure out the number of moles of that we used, 0.5062. Why did I pick such random numbers? 0.5062 times our milliliters turned into liters, 0.01658. Tells us this is a really small value, 0.00839 sig figs, looks like 4 sig figs, 8393 moles of this stuff. All right, if I look at my equation, this one's an easy one because this is a 1-to-1 reaction, right? So 1 mole of this is going to react with 1 mole of this. Our coefficients are 1 all the way across. So that I know that now I've got 0.008393 moles of this acid must have been present in this 10 milliliters, right? I could do it as a Stoic problem if you want me to, but that's the 1-to-1 ratio. So now in my vinegar, I know this. I've got 10 milliliters. I know that it's 0.008 393 moles. And now I can use my molarity equation. Molarity equals moles per liter, 0.08393 divided by 0.010. And I know what the value is. 0.010 is, our final molarity is 0.839. Well, you can see the number right there, 8393 moles per liter. So again, using titration this way is just a stoichiometry problem. It's just the wording sometimes throws students off because they're like, what in the hell are they talking about? We're literally just using a known concentration of this, finding our volume through experiment, and then knowing how it neutralizes down here. It's just a stoic problem from there. Okay, so there you go. That's some introduction to some acid-base neutralization reactions. I've also introduced the concept of what titration is. We're going to go into this one way more in depth later on. So I hope you liked it, and I will see you in class.